Okay, let me talk my way through the exercises in Activity 2. This is a written activity, so you can write on paper or put it in a document. As I've said many times, I don't grade the documents for prettiness, so please do whatever is most quick and most convenient for you. You know, in the working world and industry, time pressure is very important, so all I want is a document that's accurate, doesn't have to be pretty. If you do a Word document, you can name it Owl Theory or your last name. Okay. Now, we're going to do more with eigenvectors and eigenvalues because we saw before that these are very important in understanding the behavior. So in part A, use Wolfram alpha to compute the eigenvalues and eigenvectors. This is for the matrix in activity 1. Okay, so you have a specific PQRS, I'm sorry, a PQR in U, and that gives you a specific matrix. Okay. Now, the values that you will get 3 eigenvalues, and you will get a largest eigenvalue. And this is related to the graph that you produced in part A. All right, and I'm just going to tell you that you remember that the largest eigenvalue is related to the eventual behavior of the system. Here's a little hint here that helps you understand. If you remember the equation from spotted owl wood rat that gives the eventual behavior of the system in terms of eigenvalues and eigenvectors, you can go back there, and I hope you can make the connection between that and this hint here. Okay. All right, now for part C, I want you to use Wolfram alpha again to compute the characteristic polynomial of the general transition matrix. In fact, if you just put in the matrix, it will give you the characteristic polynomial. Okay, so that's straight from Wolfram alpha. Part D, let's call this characteristic polynomial f of x. All right, so the characteristic equation is characteristic polynomial f of x equal to 0. So the eigenvalues are the roots of f of x. Now, what I want you to do is sketch this, the graph of this polynomial. And one way to do that, it's very helpful to find the derivative. Okay, turns out that this derivative has 2 roots, and you can compute f of r1 and f of r2. Now, note that r1 and r2 are the roots of df dx. So df dx of r1 equals 0. df dx of r2 equals 0. But f of r1 and f of r2 are not 0. Now, I want you to remember from calculus, if you don't remember, look it up. What is the significance of the roots of the derivative? In other words, when the derivative of the function is 0, what does that tell you about the graph of the function? All right, that gives you some very, very important behavior of the function when you know when the derivative of the function is 0. And you can use that to make a graph of the function. Okay, so I want you to use this information to sketch the graph of f of x. You can also use the fact that p, q, r, and u are all positive real numbers that are less than 1. And also you should think about the behavior of f of x when x goes to infinity and when x goes to minus infinity. So if you put all these facts together, you can put a very good sketch of the polynomial f of x. I don't think Wolfram alpha is going to help you here. This one you're going to have to figure out on your own. Okay, maybe you can figure out some way to do it, but I think you're going to have to figure this one out on your own. All right? Now, once you have this sketch, I want to use this sketch to give an argument that the transition matrix has only one positive real eigenvalue and no negative real eigenvalues. Now remember, the eigenvalues of A are the roots of the characteristic polynomial. You can use that information to solve E. Okay, move on to F. Use your result from E to prove that A always has 2 complex eigenvalues. You can read this hint, and if you don't know this fact, you can look it up on the web. Okay. All right, now here's another fact of the eigenvalue. It turns out that the positive real eigenvalue is greater than 1 as long as this condition holds. Okay, and you can get that by computing f of 1. Now I suggest you compute f of 1 and then use that to plot another point on your graph, right? Because you know the x-coordinate is 1 and the y-coordinate is f of 1. The point 1 comma f of 1 must be on the graph of f of x. Right, so I use that information to show this result. All right, this one's a little bit challenging. This condition here, u plus pqr is greater than 1, has a practical interpretation. It has a practical meaning, and I want you to give that practical meaning. Okay? And here's a little hint to help you along. I want you to think about that one. Okay. Okay. Now, using the characteristic polynomial, which you computed, where did you compute that? You computed it somewhere up here. You computed that in D. I want you to show that the product of the three eigenvalues is equal to PQR. Here's another little hint to help you out with that one. Okay, but you can use your expression for the characteristic polynomial to show that the product of the eigenvalues is equal to PQR. Okay. Now, let's say that lambda 1 is a positive eigenvalue, and lambda 2 and lambda 3 are complex eigenvalues. Okay, because we've shown that there's one positive eigenvalue and two complex eigenvalues. Now, suppose that lambda 1 is greater than 1. Right? Now, remember, the practical significance of lambda 1 greater than 1 means that the population eventually is growing. Now, in that case, you can show that lambda 2 is less than 1 and lambda 3 is less than 1. And here I give you a little hint. You're going to do some algebra to show that lambda 1 is greater than 1. Use the result in part I. So this is all algebra. It's algebra, it's understanding the equation and knowing how to use algebra. Nothing new here. Okay? Okay. This is all college algebra. Okay? Now, from activity 7 of the Owl-Woodrat model, it follows that the solution vector, forgot the brackets here, can be written in the following way. This equation should look familiar to you. There are three terms here because we have three eigenvalues. Here's the first eigenvalue. If I'm trying to get jk or sk, ak, that's the same thing as xk. That's the state of the system at time k. Okay. Xk is equal to a linear combination of three vectors. This v1 is the first eigenvector. And when you have complex eigenvectors, the form is different. That was one of the exercises we proved. Okay. This W1 and W2 are not eigenvectors, but they are real vectors. And I can express the state vector as a linear combination of these vectors. Notice this coefficient here, r to the k cosine k theta. Now, if you treat this as a function of k, what does it do? Let's suppose r is less than 1. Okay. Now, what does this cos k theta do? Well, as k goes from 0, 1, 2, 3, 4. Okay, so here's 0, 1, 2, 3, 4, 5, 6. This cos theta is going to, if you remember the graph of cos theta, it gets a wiggle like this. So this is going to, the cos theta is going to make it wiggle. What is the r to the k going to do to your graph? Well, if r is less than 1, this is going to decrease. So we have an exponential decrease superimposed with a wiggle. We get something that looks like this. Okay. Same thing here. Here we have exponential decrease, rk, superimposed with a wiggle. The only difference here is cosine starts at 1, sine starts at 0. So we're going to get something similar. It's here, and we're going to have a wiggle that decreases like this. Okay, so we have three terms here. We know this term is growing, and these two terms are shrinking, and we have exponential with a wiggle. These two terms look like exponential with a wiggle. So if you add these two together, it's still going to look something like exponential with a wiggle. Okay. All right, here's the explanation of the terms. All right. Then I ask you to show that the long-term trend can be expressed this way. Actually, what I just mentioned is pretty much an answer, but I want you to write it out. Okay. So I want you to use this result to predict these ratios, jk over sk and sk over rk. Okay, let's see what we have here. J is the, that should be AK, I'm sorry. That should be AK there. That's JK over SK and SK over AK. Okay. And you can verify this theoretical result with the numerical results from your spreadsheet. Okay, you should be able to use this information to compute these ratios when K is large. Okay. All right, now, moving right along here, for this part, it says using your result in G. Actually, it's the result from this part here. It's the result from K. It should be a K. So I want you to compute, and so this is just algebra. You have an equation in K, and I want you to compute this vector here, the exact expression minus the trend. Okay. All right, now, part M, the last part of activity 2, from the numerical values of lambda 2 and lambda 3 in part A, use Wolfram alpha to compute R and theta. Now, R and theta are related to the two complex eigenvectors. This is called the complex polar form of the complex number lambda 2. This is the complex polar form of lambda 3. Note that these two eigenvalues are complex conjugates of each other. This is r cos theta plus ir sine theta. This is r cos theta minus ir sine theta. If you plot these two values on the complex plane, this is the real axis, this is the imaginary axis. Here we have r cos theta plus ir sine theta. That's going to be a point up here. And r cos theta minus ir sine theta, it's going to be below the real axis at the same distance. And just to give some geometrical interpretation, r is the absolute value of the complex number. Theta is called the complex argument. It's the angle in the complex plane. Okay? So I want you to compute r and compute 2 pi over theta and relate these values to the graph you produced in part B of activity 1. Okay, that's it for activity 2.